And now, please welcome Facebook Chief Technology Officer, Mike Schrepfer.
Good morning. How you guys doing? You ready to have some fun? We got some good stuff to talk about today, because today we're going to talk about the future. The future we want to create where the world is more open and connected, and what we need to do over the next decade to make that happen. When we think about this future, we think there are three core problems we need to solve. The first is we need to build services that scale to the entire planet. This means not tens of millions or hundreds of millions or billions, but services that are truly at planetary scale. And we need to connect all of those on the internet who aren't yet connected. The second core problem we need to solve is creating computer systems that understand context and information, that can help us navigate the world, that can help all of you deal with the problem you have every day, information overload. And the third thing we need to do is build immersive new technologies that truly give you a sense of presence, that can teleport you to a new place to create these shared moments, experiences, and memories with the people you care about. When you think about the progression of these technologies over the years, we've had huge advances that connect the planet together. If I wanted to send a message to New York 200 years ago, it would take me 10 days on the Pony Express. The railways took that down to 3. The telegraph introduced speed of light communication, instantaneous, coast to coast. The telephone was the first time we had a new natural interface. I picked up the receiver, I spoke into it, instead of transcribing my text to Morse code. And on the other end, the receiver, you can listen to what I'm saying. And you hear not just the words, but the content in the tonality of my voice. Am I happy? Am I sad? All of this millennia of evolution in your brain and your inner ear, allowing you to interpret the meaning of the words by the tone, by speaking into the receiver. Natural interfaces. When we added a camera to that phone, we introduced circa 2015 state-of-the-art intercontinental communication technology, video chat. It gave us just a glimmer of this third area, this sense of presence. Because not only can I hear you, I can see you, and I can see where you are. Is it sunny outside? Is it night or is it day? Is it raining? It doesn't make me feel like I'm actually there with you, but I get just that little taste of maybe I am there with you and a sense of where you are. So what we need to do over the next 10 years is really take all of these three areas, connectivity, natural interfaces, and true presence to the next level. Let's talk about what this means, starting with connectivity. Over the last 7 years, we've had to invest tremendous amounts into the core infrastructure of scaling the Facebook family of services to billions of people all across the planet. And that starts with just the foundational layer, the actual physical infrastructure. You can see here our 4 open compute data centers. These are Facebook designed, engineered, built, and owned. They are some of the most state-of-the-art data centers in the world, use technologies like free air cooling to dramatically reduce power and water use in the data center. To give you a sense of scale of these buildings, because it's a little hard to tell from these pictures, if you were to park the latest generation aircraft carrier next to one of these buildings, there's often 4 on a site, the building would be just a little bit longer. This is 1,300 feet approximately, end to end. Rows and rows of machinery down these data centers. They give us massive economies of scale. These economies of scale allow us to reliably provide Facebook to billions of people all over the world. And if you were to go inside these data centers and look at the equipment there, what you're going to see is stuff that we've built and designed. This is not just cooling and UPS and electrical systems. This is racks. These are 8 different classes of servers, storage units, and in our latest data center, a next-generation flat interconnect fabric, a network design completely built by us. And when you put all of these pieces together, we've saved at least $2 billion over the last few years just on this foundational layer, just on the hardware. And you think about that amount of savings, it is really, when we talk about connecting the planet, that sort of economies of scale is required in order to affordably build the sort of services we're talking about. And the best part about this, it's not just for us. You can use this too. 4 years ago, we introduced Open Compute, a revolutionary new idea where we took the ideas of open source software and applied them to hardware and said, here's the designs for our data centers and our servers and all the equipment in them. Let's put them together and you can use them too. And this isn't theoretical. Other people have deployed entire data centers, deployed servers. If you look at the Open Compute project 4 years later, it is the who's who of hardware manufacturers. Some of the latest entrants who have joined the Open Compute initiative are HP, Juniper, and Apple Computer. And Riot Games, when they deployed open compute infrastructure, said that they've saved about 50% in their infrastructure costs. So this is foundational technology, not just for Facebook, but for all of you, so that together we can build the services that truly scale across the planet. And this is just the hardware layer. When you move up one layer in the stack and you say, I need something to run all my application code, build applications that run in my data center, you need some sort of runtime. For us, it's HHVM, a state-of-the-art JIT-based VM for PHP. This has, between when we first deployed it and replaced Zen PHP to now, at least a 10x efficiency win for us. Dramatic increase in efficiency. And again, this is not just for us. Lots of other companies, Box, Wikipedia, have deployed HPHP. Wikipedia has seen about a 5x increase in efficiency and 50% to 2x increase in performance in many operations because we've open-sourced HHVM. It's one of our more popular open-source projects. So you've got this middle tier that allows you to build your application logic. And then on top of that, you need to actually build the front ends. You need to build the front end on the web, front end on mobile. This is where React comes in. Anyone here use React? Yeah. React is awesome. I have never seen so much excitement about a technique and a technology for building front-end applications. And again, this looks like the who's who of the internet industry. If you have used Facebook on the web, if you booked your room here on Airbnb, if you watched a movie on your TV via Netflix, you've used React and you didn't even know it. Again, this is open source. It is actually our most popular open source project now, so it's available for all of you to contribute and use. But there's been one big missing piece, and that's what we're here to announce today, which is React Native is now open source, available for all of you to use. React Native is awesome. And you've already used it if you've used many of Facebook apps because we've built it on iOS to allow us to take these same ideas for building responsive, flexible interfaces that are easy for lots of programmers to build and use it for Facebook. And open source isn't just a one-off thing for us. We have over 240 active open source projects. Almost all of them are actively deployed on Facebook infrastructure, meaning this is production code we're using, not just random stuff we create and throw out. There have been thousands of external open source contributors, and we estimate well over 10 million lines of open source code contributed by Facebook worldwide. So this is our commitment to build these services in the open with you. This is the first part, building services, software, infrastructure that scales across the planet. The second part of planetary connectivity is making sure that everyone can participate in the internet. This is the problem that all of us in this room probably take for granted. You're all here on 4G or possibly Wi-Fi, and it probably wouldn't surprise you that 4G distribution across the world isn't that broad. There's many places in the world that don't have access to 4G. You say, well, what about 3G? Yep, more people have 3G access. And even if you go back to Edge or 2G, which most of you probably haven't used for a decade, it still doesn't cover the entire planet. We'd estimate 1 to 3 billion people do not currently have access to internet data. And when you tease apart this problem and try to understand why is it that people can't get internet access, it's actually a basic lesson in economics and geography. In dense urban areas, it is economically feasible to recoup the massive capital investments telcos have to do to provide internet access. You're doing terrestrial infrastructure, where you're literally digging ditches and laying fiber or stringing fiber across poles. They're putting up cell phone towers. You're doing lots of work on the ground to provide this access. And this costs billions of dollars that you need to recoup over a large subscriber base. As you move to more rural areas of the world, you just can't recoup those costs. So what we're doing with Connectivity Labs is investing, as we have in OCP and others, in radical new approaches to this problem. And this basically means going to the sky. You have to have satellites, drones, and other things that don't require the massive investments in terrestrial infrastructure in order to affordably provide internet access for this world. This is a picture of Aquila, our first prototype for our unmanned aerial vehicle. This is a solar-powered drone built by a team who has the record for the longest ever solar-powered drone flight. The idea of this is to loiter across an area at very high altitude, 60 to 90,000 feet in the air, stand on station for months at a time, and beam down backbone internet access. From this photo, it's hard to get a sense of scale, and this is an early prototype for testing out the aerodynamics. To give you a sense of the scale of this thing, this is us actually constructing the full-scale version. This is several wing segments, so this is actually one of the wing segments. And if we were to show this thing in real life, It is the wingspan greater than a 737 plane. All of you are probably familiar with that. And it has the mass of a small car. So it's a massive wing structure with solar panels so that it can stay aloft for long periods of time. This is one of many initiatives that we're doing that we'll be able to talk in a lot more detail about later this year to provide internet connectivity for the whole world. So that's phase one. We need to get the whole world on the internet and provide all of you to build the technology needed to build services to scale. The second problem we need to solve is this information overload problem. And the most common question I get when I talk about AI is like, why is this so hard? What's this a picture of? Anyone? Dog? Right? My 21-month-old boy can nail that question. Dog. Right? To a computer, this is a confounding question. What is this? This is a series of pixels. For developers in the audience, you know what I'm talking about. Pixels are just dots. They represent individual parts of this image. Each of these pixels is typically an RGB value, red, green, blue. And to a computer, each one of these images are the same. They're just a series of numbers. They can't really tell the difference between a dog or a car or a house or a person. So the real revolution in the last few years of AI and big data is convolutional neural nets, this idea that you can teach computers to understand more hierarchical representations of images. This is one of our convolutional neural nets training on images. And what you can see is a couple different layers in the net where first it figures out that there are edges in the image, that this part of the image, me, is a little different than the background. And then it can figure out that I'm hopefully a person, not an android, a real person. And then that's the background. And you can see it's categorizing fruits, cars, wheels, other parts of the image. So you can start to build up deeper understanding of what's inside the content, not just the actual representation of it. But you can apply this not just to images, but to videos. I'd ask you, if I showed you a sports clip and asked you to tell me what kind of sport it is, how many different kinds of sports do you think you could name? A dozen, 100, 300 different sports? Kind of for fun, we said, can we build a classifier that classifies 487 different kinds of sports? So let's see this in action. So I can tell you what you're looking at here. Up on the top of the screen, you'll see the actual top 2 categories. It classifies as a number of categories, but the number 1 is what category it thinks the sport is. This is just by looking at the pixels in the video. So it's looking at the video clip and trying to figure out what kind of sport is this. So you'll see this one's basketball. It's a fairly easy one. This is the easy clips. Baseball, badminton, rafting, table tennis. These are pretty easy if you actually think about it, fairly easy to identify. As you can see, we have a very strong confidence interval. We're actually completely confident, 1.0, that this is table tennis. But the cool thing about these systems is you can get them to understand very minute differences between sports. Think about all the different sports that involve skating and hockey. When I got into this, there's more than I realized. Let's look at some of these. Ice skating, synchronized skating, figure skating, artistic roller skating, that's roller skating. Oh, that's short track speed skating. Hockey, sledge hockey, underwater hockey. I had to look that one up on Wikipedia. Got to have robot combat. I'm not sure that's really a sport, but yes, freestyle slalom skating. This is team favorite, mountain unicycling. I'll lie if I didn't watch this video a lot of times prepping for this talk. So you can really get these systems to understand deep, minute differences. What's the difference between inline roller skating and hockey and ice skating, between hockey and sledge hockey and underwater hockey, and understand them well. But the real trick we're trying to do if we're trying to understand context is not just images or video, but to really understand context and language. And before any of us get too excited about the power of AI and what we can do here, you have to realize how easy it is to trip up even the state-of-the-art systems. Let's try a really simple test. John is in the playground, Bob is in the office, John picked up the football, Bob went to the kitchen. Where's the football? Anyone? It's in the playground. Why is it in the playground? John picked up the football. Where's John? He's in the playground. For all of you, this is like well, this is a dumb question, Shrep. This is easy. For a computer, again, even the most state-of-the-art system circa 6 months ago could not reliably answer this class of questions because it requires stringing together facts it has just learned about the world. Basic convolutional neural nets are like big pattern matchers. You train them on a ton of data, and then once you're done, it's like a little box, and you feed it something, and it tells you what category it is. But when you teach it new things about the world and you feed it new facts, it doesn't learn. It doesn't have a memory. Let's try another one. John is in the playground. This is even easier. Daniel picks up the milk. Is John in the classroom? No, I just told you he's in the playground, right? simple question. Again, confounds most traditional AI systems state of the art. So our team took a new approach. They built a new system, and they called it the memory network. They take the power of a convolutional neural net, and they attach onto it a multi-million slot memory system that can learn real-time facts and then answer questions based on them. Let's see this in action. Sorry for the small font, because we're actually capturing, this is Antoine, who just wrote this paper. This is dev server on Friday. We know this is real because he accidentally deleted the training network and had to retrain it. But we're actually doing a screen cap from his from Torch, which is the system we've open sourced to build AI systems, on his dev server on Friday. And what we're doing is this memory neural net has a short-term memory, so you can answer questions on facts it's just seen. And so we like Lord of the Rings. Everyone likes Lord of the Rings, right? So we fed it a very cribbed version of the Lord of the Rings. If you can see this in the audience, it's kind of Bilbo went to the cave, Gollum dropped the ring, Bilbo took the ring, went to the Shire, Frodo got the ring, went to Mount Doom, dropped it there, went back home. You know, kind of the quick Cliff Notes version of the Lord of the Rings. Misses all the cool battles, but, you know, it's a computer. So prior to seeing this text, this system knew nothing about the Lord of the Rings. It was not trained on classics. It wasn't read a corpus of Tolkien. It just has seen this for the first time right before we answer this next command, and we start asking it similar questions you just saw. Things like, where's the ring? Again, you have to understand that Frodo had it, he went to Mount Doom, and he dropped it there, and so it's at Mount Doom. Well, what happened before that? Well, Bilbo had it before that, and he was in the Shire, so the ring was in the Shire. And then where is Frodo now? Well, he went back to the Shire. So you can see complex chaining of facts together, understanding of time and relationship between objects and time. This is a true breakthrough in what we're doing in artificial intelligence. All right, so the next question I get, the first question I always get is like, why is this so hard? Second question I get, I've shown this to a lot of people at work, and they're all like, sweet demo, Shrep. What the heck does this have to do with Facebook? Like, cool, Lord of the Rings, I get it. I don't understand. And that's where this comes in. When you think about the problem we're trying to solve, all of you have seen this. We had our data scientists do a very deep study in the content production of cat videos on the internet. They've determined after extensive study that it's exponential in terms of the growth of cat videos on the internet. And breaking news, the amount of hours in your day is constant. This is the attention problem. Y'all are supposed to laugh there, but that's all right. Everyone knows why engineers aren't good at jokes timing? All right. So, in all seriousness, if we achieve our first goal, get everyone on the internet, build services that scale to the entire planet, we create this new problem. So much information, you can't consume the stuff that's important to you. We want you to spend every minute of your day and have control over what you look at and what you see and what you interact with. A great life is where you can spend the time on the things you want and, most importantly, with the people you want. And by building systems that understand the context of the world, understand what it is you want, we can help you there. And we can build these systems that make sure all of us spend time on the things we care about. That's the promise of applying AI to something like Facebook. All right. So we've got everyone on the internet, we've got systems that help you navigate what's going on. We're missing one key part, this sense of presence. This is VR. This is Developer Kit 2, the Oculus, current shipping developer kit for Oculus. They've sold a few 100,000 of these to developers all over the world. Many of you may have some at home. And similar to AI, the question we asked ourselves when we looked at VR is, well, VR is awesome. I mean, I've always wanted VR, haven't you? But why is it going to work now when it didn't work in the 80s or 90s or 2000s? And when you look at it, you realize what was required to make VR work now is that every core component that's part of VR, this is, if you look at the Developer Kit 2, you've got integrated circuits and IMUs and gyros to track location. You've got a high-resolution screen. You've got a high-resolution, high-performance camera to do 6-degree of freedom tracking so you can see where the head is positioned at any one point in time. And you've got to manufacture all of this at a cost that's reasonable for a consumer to buy. And so each one of these core tracks of technology had to hit a minimum bar of viability so that we could assemble them together and build the entire system that is VR to get to that goal of presence, that sense that you are truly there. This is one of the first VR games, 1980, Battlezone. Did anyone play this? Yeah. If you remember, it was like a big stand-up arcade thing, and it had like a pair of goggles you'd look in. You kind of stare and you look in it. And for those of you who haven't played, you are immersed in feeling like you are driving a tank, right? Anyone feel like they're actually driving a tank right now? This is state-of-the-art 1980s vector graphics with equivalently state-of-the-art beep-boop-bop sound going next to it. And I tell you, in the 1980s, if I had invented a magic pair of goggles that perfectly injected photons in the real world into your eyes, and I powered it with something like this and said, you're in a tank, there's not a second that would go by that you would think you were actually there. Let's see what we can do with 2015 consumer technology. So this next demo is a game under development. The film here is actually shot in the Oculus. So all of the camera motions you're seeing is actually someone playing this game in real time on a PC with hardware you can buy today, looking around. As they look around in the Oculus, you're seeing the camera move. Let's see what this looks like.
Welcome, pilot. Begin systems check. Navigation systems online. Rockets online. Engines online. Magnetic catapult initialized.
Hold on tight, we're ready to deploy.
Launching in 3, 2, 1.
Listen up, this is Lieutenant Havoc.
Anyone else get out of their seat when you got out of that catapult at the end? I swear, I've watched this video a lot too. This is amazing. You're going to be able to do this year in VR. This is going to be incredible. And you're going to be doing it in something shipped by Oculus. This is Crescent Bay, the latest prototype of what we're building to build VR. We've shown this here. Hopefully many of you have gotten a chance to see it in the Oculus booth in the building next door. If you haven't seen it here, you might have seen it at Game Developer Conference or CES. We've shown this to thousands of people. And just like here, people are waiting in lines, this is at CES, for hours at a time in order to see the magic of presence and the magic of VR. And after thousands of demos, we know we are just on the cusp, just getting there, to get that sense of presence, where for a moment, your conscious brain is overruled by your subconscious, which says you are not where you think you are. When you're standing on the top of the building, you can't step forward when I tell you to, even though you're in a room and not in a building. So we know we're just getting to that minimum bar of presence this year with what we can build with VR technology. Okay, again, sweet demo, Shrep. What the heck does this have to do with Facebook? VR is awesome. Why is Facebook talking about this? That's the very next question I always get whenever we're talking about this. And I'd ask you this. So by show of hands, how many in the audience, when you go out to the movies, do you usually go by yourself? Not very many, right? A few. Yeah. Yeah. Look, we're nerds. It's okay. This is a safe place. Why the heck do we go to a closed room where I can't interact with someone next to me, sit there for 2 hours and stare at a screen? Why do we do that with someone else? Why don't we go alone? Because we're creating a moment, an experience, a shared memory. On the way to the theater, can't wait to see the last installment of The Lord of the Rings. On the way home, can you believe that fight scene at the end? It is a moment in time where you and your friends or loved ones were together in a space, and you had that experience. Those moments where we're bringing people together is what we are trying to do at Facebook. It's the core of our mission. You've all experienced this in a very small way on your birthday on Facebook. I had a birthday recently, and I had this moment where people from all over my life, from school to work to family, celebrated my birthday with me. And I got a surprise when I came to work. Mark made me blow out one candle for every year I was old, which gets harder every year. Let's see what this looks like. Yeah, barely made it. Got to work on that lung capacity for next year. It was a fun moment. So a reverent, fun little moment. It was a surprise. So lots of people I care about weren't there to celebrate it with me. But thanks to Facebook, they could. We shared the video. They all could see it and participate in it with me. But these moments in life that are amazing and you want to bring everyone in with you towards happen all the time, not just on birthdays. Any parent in the room knows this happens all the time. Just this weekend, Sunday, my 4-year-old rode for the first time without her training wheels. It's an amazing event. And it's one of those moments where I wanted everyone. I wanted her grandparents, her nieces, her nephews, her uncles and aunts. I wished everyone could have been teleported to that moment. And so the real power of marrying this technology that gives you this sense of presence and being in a time and place with someone, and the most powerful, most used social connection platform in the world, Facebook, together, is our ability to bring everyone into these moments at one point in time and to have this true sense like you were there. That's our hope with what we can do with VR. So that's our goal over the next 10 years. We're going to connect the world. We're going to build systems that help you manage all of that information and connectivity. And we're going to build technology that fundamentally brings people together. I think it's going to be fun. I'm pretty excited about the next 10 years. It's going to be crazy, fun. And I'm very, very happy to have all of you along with us. As we have in all of these technologies, we're going to be working with all of you to bring this future about that betters all of us. With that, it is my great honor and pleasure to introduce Michael Abrash, Chief Scientist, Oculus.
Good morning. I have to tell you that for me, being here is one of the most astonishing events in a life that's had more than its share of them. Even 3 years ago, the idea that in 2015, I'd be giving a keynote on virtual reality to tens of thousands of people at F8 wouldn't just have been science fiction, it would have been pure fantasy. VR had been dead and buried for more than a decade and seemed no closer to broad success in 2012 than it had 25 years earlier. And yet, amazingly, here we are. Recently, I took some time to think about how I'd come to this remarkable point, and I realized the thread ran a long way back. The roots clearly lay in a lifetime of reading science fiction, which showed me the path to thinking about VR as not only possible, but as something that I personally could help to make happen. In particular, Neil Stephenson's Snow Crash helped me see that virtual worlds were possible way back in 1994, and more recently, Ernest Cline's Ready Player One painted a compelling picture of what VR could be with some breakthroughs and a lot of hard work. What I also realized, though, was that while science fiction novels gave me the conceptual framework for thinking about VR, it was The Matrix that made me believe in it. Even though it was based on technology that won't exist for decades, if ever, The Matrix gave me a deep sense of what VR could someday be like. Not only how real it could be, but also how exciting it would be to bend and stretch that reality. So I went back and watched The Matrix again, and it was just as fun and inspiring as I had remembered. What I hadn't remembered, though, is that just before we learn that humans are batteries, there's a speech by Morpheus that does a remarkably concise job of summing up what it is that's truly unique about VR. Here's that speech. What is real? How do you define real? If you are talking about what you can feel, what you can smell, what you can taste and see, then real is simply electrical signals interpreted by your brain. That's really all you need to know to understand why VR is not just cool, but world-changing, and why you are going to care a lot about VR sooner or later. Let's dive into the implications of Morpheus' speech. The place to start is with understanding what virtual reality really is. Most people focus on the virtual part of virtual reality, meaning artificially generated inputs to the perceptual system. However, the right place to focus is on the second word, reality. Morpheus asked the question that's at the heart of today's talk, what is real? Then answered his own question with, real is simply electrical signals interpreted by the brain. He made two critical points with that sentence. The one most people pick up on is that we, our conscious minds, never actually interact with the real world. Instead, we interact with signals from sensors in our eyes, in our ears, in our skin, on our tongue, in our nose, in our balance organs, and throughout our body. We only know what those sensors detect, interpret, and signal to the brain. And that's actually a very small subset of the real world. Consider vision. We can't see infrared or ultraviolet. We only have 3 color sensors. We only see about a 2-degree circle in high resolution. We have a blind spot in each eye. We can only see a fraction of the full 360 degrees around us in every direction at one time. We have no blue photoreceptors in the center of our vision, and a large blind spot straight ahead at night. And everything but the plane we're focusing on is blurry. Rich as it seems to be, our visual data is actually astonishingly sparse. But even if we were able to accurately record the magnitude and direction of every photon that reached our eyes, we'd still have far too little data to be able to reconstruct the world accurately. For example, I'm pretty sure most of you have seen the dress. Is this a blue and black dress in yellow light, or a white and gold dress in blue light? Given the photons reaching your eyes, it's an unsolvable problem. No passive sensor is capable of resolving that ambiguity. In order to form a coherent model of the world, our perceptual system has to make assumptions and send its best guess to the conscious mind. And this particular picture is so ambiguous that some people see it one way and some the other. It's noteworthy how deeply certain people are about whichever guess their perceptual system makes. They just know they're right. And here we come to the second and less noted part of Morpheus's definition of reality. Real is just electrical signals interpreted by the brain. The way the brain compensates for the limited data it receives is by maintaining a model of the real world that it constantly updates as new data comes in. And it is that model, not the real world, that you actually experience and trust implicitly. Don't believe it? If you're experiencing the real world right now, why can't you see your blind spot? Why aren't you aware that you can't see blue straight ahead? Why can't you tell that you're only seeing an area about the size of your thumb in high resolution? It's because your brain has a model that fills in those gaps with its best guess at the state of the world at every moment. And it's that model that you actually see, hear, feel, smell, and taste. At the core of the reality that each and every one of us experiences lies the fact that we're inference machines, not objective observers. By which I mean that there is, presumably, a real world out there. And your brain is taking the very limited signals coming from your sensors and trying to infer what the state of that real world is based on its internal model. It's one thing to listen to words about how we infer reality, but it's another matter to actually experience it. So let's look at an example where the inference mechanism breaks down. Something is not right here. But what? I'll explain this later, but the key point is that what you see in this video is ambiguous with multiple valid solutions, and your perceptual system has chosen the wrong solution based on a set of assumptions that's almost always correct. The same process happens every waking second of your life. The only difference is that you normally infer the correct solution to the state of the world. The fact that reality is whatever your mind infers from the nerve impulses sent by your sensors based on its model of the world is at the heart of what makes VR different and more powerful than anything that has come before. It's so important that I'm going to spend a few minutes giving you a deeper sense of how ambiguous the world really is as observed through our various sensors, and the extent to which reality is constructed by our minds rather than recorded by our senses. Where better to start than by choosing between a red pill and a blue pill? Unlike Morpheus, I'm not offering you a choice today. No matter which color you pick, we're all headed down the rabbit hole together. So pick a pill and keep your eyes on it. Got it? Let's mask off everything else. Interesting. You were pretty sure that out there in the real world, one pill was red and one was blue. But they're exactly the same shade of gray. The colors you saw were entirely constructed by your perceptual system, and existed nowhere else. In fact, let's look at the original slide again. What color are the pills now? It doesn't even make any difference that you know they're both gray. You still see red and blue. So what does that say about how well your perceptions correspond to the real world? Welcome to the rabbit hole. And yes, I know it looks like I photoshopped this slide. By definition, it's hard to show you visual illusions that don't look photoshopped. So your packet contains a physical version of the pills that you can check out later and verify that I'm not cheating. Let's look at some other illusions and what they tell us about how we perceive reality. Some of these may not work perfectly for some of you. It's a bit unpredictable doing illusions on a big screen, but they should work well enough to make the important points. Take a good look at the blue tiles on top of the left cube. Okay, now take a good look at the yellow tiles on top of the right cube. You think those are colors you're seeing now? Let's mask off everything but those particular tiles. They're all exactly the same shade of gray. This is similar to the pill illusion we just saw, but it's clearer here what's happening. Your visual system isn't interested in whether the photons coming from a tile in a random image are red or blue or gray. Knowing that didn't keep anyone from being eaten by lions on the savannah. What it is interested in is identifying potentially relevant features in the real world under a variety of conditions. When you look at an object, what your eye gets to work with is an approximation of the spatial distribution of wavelengths of light. But what your brain cares about is the actual color of the object. So your visual system constantly corrects for the lighting in a scene. Given the apparent lighting in this scene, the best guess is that the left tiles are blue and the right tiles are yellow. Here's another example that shows that your visual system is reverse engineering reality rather than just recording it, this time involving brightness. See the white tile under the desk and the black tiles just outside the desk? Again, let's mask off everything else. And again, they're both exactly the same shade of gray. But if one of them is in shadow and is that shade of gray, it must be white. And if another one is in bright light and is that shade of gray, it must be black. Your visual system does the inference for you automatically, and what you see is white and black rather than gray. Let's look at how we perceive form next. Here we have a nice square checkerboard. Let's add some dots and see what happens. This happens because some line detectors fire that normally wouldn't be triggered by a checkerboard. When we have a regular checkerboard, your visual system deploys cells with sensitivity to contrast edges at various orientations, represented by this starburst. And of those, it detects high contrast edges at exactly two orientations, the horizontal and the vertical. So you see right angles, as you'd expect. But if we switch to the bulging checkerboard image and deploy the same perceptual mechanisms to detect orientation, your visual system detects high contrast not only at the horizontal and vertical orientations, but also on slightly slanted axes as well. As a result, the perceived orientation is skewed. Rather than looking orthogonal, the corners look bowed. The checkerboard is a 2D demonstration. Next, let's straddle 2D and 3D. Take a moment and figure out which of the two tabletops in blue is wider as measured in 2D and which is longer, assuming you rotated them to line up. Ready? They're exactly the same size. Think the shape morphed while it moved? So did I the first time I saw it. So let's do this. Take the shepherd's table figure out of your packet. Punch the left-hand table out of the paper and place it over the right-hand table. I'll wait. If you haven't gotten there yet, you can always do this later. Trust me, they are indeed the same size. We live in a 3D world, and the 3D objects implied by the 2D shapes of the tables are quite different from each other. Your brain does this calculation automatically for you, making the assumption that you're looking at a 3D world. That's wrong in the specific case of trying to compare 2D table sizes here, but in general, it allows us to function in a 3D world, which is, after all, where we happen to live. Of course, the world isn't static, so perceiving motion is critical. And while you might think motion is surely simply observation of the world, something is either moving or not moving, right? It is, in fact, where the underlying inferential nature of reality really shows through. Fixate on the yellow dot and observe which way the black and white dots are rotating around it. Next, look at the blue dot, and while continuing to look at the blue dot, see out of the corner of your eye which way the black and white dots are going around the yellow dot now. Move your eyes back and forth, and you'll see the rotational directions change, even though they're not actually changing. If that doesn't work for you, look at either dot, then move your eyes up until you see the direction change. Motion detection takes its cues from the highest frequency, that is, most detailed elements of the scene. And when the dots are focused near the fovea, the high-resolution part of your retina, the sharp circular edges are the highest frequency components, so the movement of the dots drives motion detection. Away from the fovea, however, there's not enough resolution to pick up those edges clearly, so motion detection is based on the movement of the lower frequency patterns within each dot. Here we can clearly see the interaction of the particular design of your visual sensors with your motion detection mechanisms. Most of the time, the two work harmoniously together, but this example shows that that relationship only holds under certain conditions. The next example is an even more striking illustration of this. Here's a video of a carnival ride. Now, take the dark film out of your packet, put it over your left eye like this, making sure to keep both eyes open, and look at the video again. Pay particular attention to the chairs, especially as they pass in front of the carousel. Remember, hold the film in front of your left eye and keep both eyes open. The chair should pop out toward you like watching a 3D movie. It doesn't work for everyone, but most people can see the effect clearly. You can also see an interesting 3D effect as the chairs cross the trees at the lower right. The reason for this 3D effect is a fascinating glimpse into our perceptual machinery. The less light the retina is receiving, the slower the eye is to send a signal to the brain. As a result of the dark filter, your left eye is signaling the brain later than your right eye. That means the signal from frame N of the video reaches the visual cortex from the right eye earlier than frame N from the left eye. Since your depth perception depends on the relative positions of objects between the two eyes, this delay of the left eye's signal means objects moving right to left appear to be nearer and vice versa. Since the nearer objects in this scene are in fact moving right to left and the farther objects left to right, they pop out as 3D, a phenomenon known as the Pulfrich effect. Now let's go back to the first illusion we saw, the Ames window. Of course, the straw isn't really going through the window. What's happening here is that you're making a very reasonable assumption about the world that happens to be wrong. There are a number of cues on the window that imply a perspective that doesn't exist. So your visual system infers that the window is spinning backward for half of a full rotation. As a result, the straw seems to rotate right through the window. This doesn't match any reasonable model of reality, so you end up seeing something impossible. The next example also makes a wrong assumption, but doesn't wind up with an impossible solution, just an incorrect one. Okay, that's just weird. Here's what's actually happening. Real objects, especially faces, tend to be convex. So your visual system assumes convexity in the absence of cues to the contrary. The only way to make that assumption work in this case is for the head to be moving in very odd ways. So that's exactly what you see. As the oracle might say, here's what's really going to bake your noodle later on. Now that you know what's happening, try to see the dragon as it really is. I bet you can't do it. A little bit of conscious knowledge isn't going to undo millions of years of evolution and a lifetime of looking at faces. There are many other visual illusions, as well as all sorts of audio, touch, smell, taste, motion, orientation, and balance illusions. These tell us a great deal about our perceptual system, but our model of the world is constructed out of many inputs across all our senses, so multi-sense illusions are even more revealing about the inferential nature of reality. We only have time to look at one of these, the McGurk Effect, but it's one of the best demonstrations I've seen of how we construct reality.
Bar, 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 bar.
Obviously, she's saying bar, bar, bar. Now let's watch a slightly different video.
Bar, 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 bar.
Here we can clearly hear her saying far, far, far. Except that she isn't. The video shows her saying far, but the audio track is still of her saying bar exactly as she did in the first video. The visual input overrode the audio. To make it crystal clear what's going on, let's look at this one more time. Once again, we'll have a soundtrack that says bar, but this time we'll have a split screen with a face saying far on one side and a face saying bar on the other. As this plays, move your eyes from one side to the other and observe how what you hear changes.
Bar, 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 bar.
The McGurk Effect is an emphatic answer to the question, what is real? What you hear depends on what you're looking at, not just at the sounds hitting your eardrums. You aren't a microphone, you're an inference machine that integrates all available evidence to construct the most likely model of the world. In short, reality is what our brain reconstructs it to be, based on our model of the world and the sparse data coming in from our senses. I think it's fair to say that our experience of the world is an illusion, one that evolution has honed to be highly functional in terms of survival and reproduction. Since the primary objective of the perceptual system as it evolved was to stay alive, it operates rapidly and automatically. As the McGurk Effect demonstrates, given a particular set of inputs, we have very little conscious choice about the reality we'll experience. That's why the rare cases where you actually can choose the experience stand out, like this Necker cube, where you can flip between looking at a cube from above and from below. Which brings us back to virtual reality and why it's different from anything that's come before. VR is about experiencing a virtual world as real. And what we've just learned is that an experience is real to the extent it convinces your perceptual system and brain, because experiences are nothing more or less than whatever your mind infers from the data it receives. And our perceptual system does that inference automatically, regardless of what the conscious mind knows. What that means is that virtual reality, done right, truly is reality as far as the observer is concerned. So what does it take to do virtual reality right? As it turns out, virtual reality doesn't have to replicate the real world in order to work. It just has to provide the right inputs in order to satisfy the relevant sensors and drive the correct inference. To paraphrase Morpheus, some rules can be bent, others can be broken. For example, many of you will get to experience the demo of the latest iteration of the Rift, Crescent Bay, during F8. When you do, I'm confident that most of you will feel like you've been teleported into a virtual world, like you're literally there. And yet, when you're using Crescent Bay, you're looking at photons coming from pixels strobed at 90 hertz, rather than photons continuously arriving from real-world surfaces and lights. That works because the period during which the receptive fields on the retina accumulate photons is about 20 milliseconds. And the structure of those fields is such that they respond just as well to the photons arriving in several short bursts as they do to them arriving continuously from real-world surfaces. Drop the frame rate to 60 hertz, however, and those same receptive fields will start to detect flicker. Drop it to 10 hertz, and motion will cease to appear smooth. In fact, Crescent Bay's display system differs from the real world in many ways. But by taking advantage of the physiology of the visual system, it nonetheless produces the desired signals to the brain. So part of making virtual reality work is learning how our sensors can and can't be driven to send the right signals to the brain. The other, less obvious part is learning what it takes to get the brain to make a desired inference. For example, remember this? We were able to get the brain to infer a face shape and the corresponding head movement by leveraging the convexity assumption. The same sort of thing is required in a general sense in order for VR to work. And the key to that is agreement between multiple senses and our internal model of reality, especially when it involves feedback loops. For example, without revealing too much for those of you who haven't experienced it yet, for many people, the defining moment in the Crescent Bay demo is finding themselves on the edge of a long drop. The response is often to grab a nearby virtual pipe, which shows that enough unconscious inference is kicked in to trigger the automatic responses that means the brain believes it's someplace real. Why does that happen? While the scene where Neo climbs out onto a ledge outside a building and looks down 1,000 feet never makes anyone grab for support. The difference is that when you move your head in Crescent Bay, both the motion your vestibular organs report and the parallax your visual system report match the motor signals you sent in your neck muscles and your sense of proprioception. That is, your model of the position of your body. And they do so with low enough latency so that your brain can fuse all those data points into a coherent model of the world. At the core of this is a feedback loop. You move your head, and what you see changes correctly and with an almost imperceptible delay, allowing your brain to maintain the same kind of model of the virtual world as it does for the real world, which then leads smoothly to further motion. That's the fundamental difference between movies and VR. Movies provide similar images, but with no feedback loop for head motion. As a result, we perceive movies as moving pictures on a flat surface, still firmly embedded in the real world. Good VR, in contrast, isn't perceived as pictures at all. It replaces rather than augments the real world. VR is about driving our perceptions the way they're built to be driven. If we can do that, it should be completely unsurprising that it enables us to create new realities. If the technology becomes good enough, VR should theoretically be able, in the limit, to create not only any experience that's possible in the real world, but any experience that we're capable of having. That's most certainly not the case today, as is obvious as soon as you reach out for that pipe and it's not really there. VR today is good enough to create experiences, but just barely. In fact, one reason the future of VR is so bright is that there are so many ways it can get much, much better. Let's take a quick look at some of the most important areas for improvement. Since we were talking about the pipe, let's start with haptics. The feedback loop I described earlier was about perceiving the world. The second key feedback loop is the one that allows the use of the hands as dexterous manipulators, as sensors and manipulators. Right now, virtual interaction is limited to gamepads and wands, which are nothing like the way we interact with the real world. It's going to take time and some breakthroughs, but I expect hands to eventually be as capable in VR as they are in the real world. Visuals will get much, much better in terms of pixel density, field of view, dynamic range, image quality, and variable focus. And while all that is improving, form factor and ergonomics will get a lot better too. To give you just one example of how much better visuals can get, in order for Crescent Bay to deliver the same pixel density as a monitor at a normal viewing distance, it would have to have a resolution of about 5K by 5K per eye, something like 20 times as many pixels as it currently has. In order for it to have retinal resolution across a field of view of 180 degrees, it would have to have something on the order of 16K by 16K resolution, roughly 200 times as many pixels. VR audio is going to get a lot better fast. Unlike most aspects of VR, no hardware breakthroughs are needed to make this happen, just a lot of compute power and the motivation to figure out how to bring audio spatialization and propagation to consumer products. And VR creates that motivation in a big way. VR computer vision and tracking are going to evolve rapidly in a number of ways. Tracking the human body is obviously critical. Virtual worlds won't seem fully real until you can see your own body. And you won't truly feel like you're sharing an experience with others until your brain accepts their avatars as people, which means tracking eyes, faces, hands, and bodies. I expect that you'll also be able to pull the real world into VR. You'll want to be able to import your coffee cup so you can pick it up without taking off your headset. And ultimately, you'll want to be able to see your keyboard and mouse so you can use them in an infinitely configurable virtual workspace. Finally, you'll be able to map your surroundings so you can stand up and walk around. Surprisingly little is understood about the human perceptual system, and even less is known about how to drive it. It's easy for me to casually say that we'll be able to use our hands as dexterous manipulators, but in fact, the science and engineering of that are embryonic. Almost all of the advances I've described require much deeper understanding than currently exists, followed by radically new technology. So why am I so convinced that VR is going to succeed this time around? The first reason is that VR is already far enough along to enable compelling experiences on consumer hardware, as Crescent Bay makes clear, and will be shipping in quantity before long. The second reason is that there are at least 4 major efforts to ship good consumer VR within a year or two. When Oculus, Samsung, Sony, and Valve/HTC are all jumping into a market, it's a pretty good bet that there's something important going on. The third reason is that developing better VR technology is hard and will require long-term commitment. Facebook's acquisition of Oculus was an important moment for this. Once that happened, there was no longer any doubt about whether VR would get the runway it needed to fulfill its potential. The final reason is the march of technology. This was my first computer, a 4 megahertz Z80-based vector graphics VIP system, for the bargain price of $6,000. Pretty sweet, huh? It didn't have a floating point unit, so let's generously estimate it at 7 kiloflops. NVIDIA just announced the Titan X, a desktop graphics card that delivers 7 teraflops, a performance increase of about 1 billion times in about 33 years. That's how technology marches forward when there's competition and a compelling reason, and that's what's going to happen with VR. In short, a lot of powerful forces are coming together right now to make VR happen. And with that, we've come to the end of our lightning tour of why VR has the potential to be a unique, transformational technology and why I think it's going to take off over the next few years. So what does it all mean? Cypher summed it up nicely. It means buckle your seatbelt, Dorothy, because Kansas is going bye-bye. Every decade or so, Kansas goes bye-bye in the digital world, and everything changes. Over the past 50 years, that progression has taken us from mini computers to personal computers to GUIs to the web to mobile. So what's next? It probably won't surprise you that I think VR is the leading candidate to be the next entry in that table, and maybe even more than that. VR is more than just another platform. In the long run, it has the potential to create the whole range of human experience. And while it'll be a very long time before all of that potential is fulfilled, the process is well underway. The shift to virtual reality is going to bring huge changes, both for us as developers and for society as a whole. If you think about the implications for work, gaming, and social networking of being able to experience whatever you want with anyone in the world, in any space you can imagine, it's clear that VR has the potential to change almost everything about the way we live. Lots of important pieces aren't in place yet. No one even knows the right locomotion mechanisms or input conventions, let alone how VR movies will work, or what the equivalent of the Facebook wall will be, or what kind of games people will want to play in VR, or, most important in my opinion, how people will want to interact virtually with each other. But all that will get figured out, a process that will open up huge opportunities. And all of us in this room are lucky enough to have a chance to play a part in making it happen. The interesting question is how long it'll be before you personally decide to make the jump to VR. Maybe you'll want to be on the leading edge. Maybe you'll wait for the technology to prove itself. But VR is potentially world-changing and incredibly cool, and it's really happening, so sooner or later, you will want to be a part of it. I'm hoping it's sooner. Thank you.